Hi there! In this video I will demonstrate how linear algebra can help solving a system of differential equations. Why now? Well, it turns out that eigenvalues and eigenvectors play an important role. The numerical example I will completely solve is the system on the slide of two differential equations for functions x1 and x2. As you can see, it can also be written in matrix form. Written in this form, it is very similar to the linear differential equation y prime equals a times yt, where a is some constant. The general solution of this differential equation is given by yt equals c times e to the power a times t. And you have also seen that the second order linear differential equation y double prime minus 3y minus 4y equals 0 has as general solution an arbitrary linear combination of e to the power 4t and e to the power minus 1t. Recall that the two coefficients minus 1 and 4 are the solutions of the characteristic equation. It seems a good idea for the system to look for solutions involving linear combinations of exponentials as well. Now, which exponentials would work? We can write the solution proposed on the slide in vector form. Note that v is a constant vector here. As you can see, differentiation then takes place component-wise, and you also see that the derivative is a constant multiple of the original vector function. So if we plug xt equals v times e to the power lambda t into the system in matrix form, we find that v and lambda have to satisfy an equation of which both sides can be divided by e to the power lambda t. This is allowed since the exponential function is never 0. We find that lambda and v have to satisfy a times v equals lambda times v. Hey, where did we see this before? That's about eigenvalues and eigenvectors, isn't it? Let's apply it to the numerical example. For the matrix A, the eigenvalues are the zeros of the characteristic polynomial. Characteristic, hey, there's that word again. So lambda squared minus lambda minus 2 should equal 0. We see that the eigenvalues are lambda 1 equals 2 and lambda 2 equals minus 1. You should be able to find the corresponding eigenvectors yourself. For lambda equals 2, we can take the vector 2, 1, and for lambda equals minus 1, the vector 1, 2 does the trick. For the system x prime equals a times x, we thus find two different solutions. 1, 2 times e to the power minus t, and 2, 1 times e to the power 2t. Note that the solutions are linearly independent, which in this case means that neither of the vector functions is a multiple of the other. Because the system x prime equals a times x is a linear system, it follows from elementary properties of matrix multiplication and differentiation that every linear combination is a solution as well. In fact, these are all possible solutions, but this I will not prove here. So the general solution becomes as shown here. If you want a solution starting from a given position x0 at t equals 0, you have to solve c1 v1 plus c2 v2 equals x0. Note that the exponentials simplify to e to the 0 equals 1. Since the vectors v1 and v2 are independent, this uniquely determines c1 and c2 for any initial position x0. Alright, we have an analytic expression for the solutions, but we also want to understand the global behavior of the solutions as time evolves. In other words, how do the solution curves look in the plane? Take a look at the general solution again. If neither of the coefficients c1, c2 equals 0, then if t goes to infinity, the term with the negative exponent will die out, and the other term gets larger and larger. So the solution will go to infinity with a line generated by v1, which is the eigenvector corresponding to the positive eigenvalue, as an asymptote. Likewise, if t goes to minus infinity, which is like going back in time, the line in the direction of the other eigenvector is an asymptote. The picture shows the general behavior. The origin is in the center. If either of the constants equals 0, we get solutions that stay on one of the lines of the eigenvectors. Especially, there are two exceptional solutions that approach the origin over the line corresponding to the negative eigenvalue. These are the red ones. For solutions showing this behavior, the origin is called a saddle point. It arises whenever the matrix has both a positive and a negative eigenvalue. For 2×2 matrices with two different eigenvalues, there are two other situations. In the case where the matrix A has two positive eigenvalues, λ1 and λ2, say λ2 larger than λ1, we again find that the general solution is a linear combination of two solutions containing the eigenvalues and the eigenvectors. In this case, every solution will run away to infinity if t goes to infinity. The term with the smallest eigenvalue is relatively small, so the direction becomes mainly that of the eigenvector belonging to the largest eigenvalue. If t goes to -infinity, the solutions converge to the origin. And apart from the solution where the coefficient C1 equals 0, the term with the smallest eigenvalue, λ1, determines the direction. In this case, the origin is called an unstable node, or a repeller. It repels solutions. We now get a picture like this. From the origin, solutions leave in the direction of the orange eigenvector belonging to the smallest eigenvalue and turn away in the direction of the red eigenvector. If both eigenvalues are negative, the origin is a stable node, and you get the right picture by just reversing the arrows. In class you will learn how to handle the situation with complex eigenvalues. So you see, eigenvalues and eigenvectors rule this world. Thank you for your attention. Goodbye.